Hello students, I am Dr. Maya Dunne. I am here to explain you about, let me go down. I'm here to explain you about the atoms and the periodic table. This is our chapter 2. First in the video, this chapter 2 video is two parts. First part I talk about atoms and the second part is periodic table. So when you go to the atoms, what is overview that you need to know? You need to know about what is the atom and then the subatomic particles and some history. It's interesting, right, to know the history of chemistry. It's interesting how the scientists discovered the electrons, what are the experiments they did, and then the nuclear model. It's very important even today. We use the nuclear model. And then we talk about the atomic number, mass number, and the isotopes. And then the atomic mass is another important area. So in atom, atom is the smallest quantity of matter, an element made out of so many atoms. Atom is, if I give you another description, atom is the smallest particle that has the properties of each element. So many atoms combine and make these elements. Example, gold. Gold made out of so many gold atoms, or oxygen made out of so many oxygen atoms. So this is the atoms. So the Dalton is one scientist who did a lot of research, and this is actually the Dalton's atomic theory. What are the important information we can get from this Dalton's atomic theory? John Dalton said that atoms, of which all the matter consists, are tiny, indivisible particles. Their tiny atoms are very tiny, indivisible particles. So, but if you get an atom, you can break atom into another smaller pieces. We call that, but those pieces doesn't have the properties of any element. So, so the nature and the number of subatomic particles determine the properties of atom, which already determine the properties of the material. That means each atom is different. How each atom is different? By number of subatomic particles. So each has different subatomic particles, so that is different atom. These atoms make elements, so elements has different properties. So this is the cathode ray experiment. I'm not going to ask you in the exam, okay, write the cathode ray experiment. No. So this cathode ray experiment used to determine some properties of these subatomic particles, including the size of an electron and charge of an electron. So so this is the experiment, okay? J.J. Thomson, he's a scientist who lived in 1856 and 1940. He did the cathode ray experiment. What he did, he passed the cathode ray in the tube and he noticed that they're going in the straight lines. So using this experiment, he identified, okay, the cathode rays, they're negatively charged. They're coming from originated from cathode and they're going to anode. That means cathode ray, so the atom has the small tiny particles. They're going from the atom has electrons. Electrons are negatively charged and they are attracted to the positive end. And then what did he do here is he put a magnet, the positive end of the magnet, and it's attracted to the positive end. So that means these particles attracted to the positive end means these electrons are negatively charged. So Thomson's contribution, they are actually, and the negatively charged particles, they're called electrons. And they're very small, like very minute. And then the Millikan is another scientist, he found a charge of an electron. So the mass of an electron, the actual electron discovered by J.J. Thomson, and he also discovered its negative, and then the Millikan find the um, charge of an electron, which is negative. C is for Coulomb. Okay. And then, so then the radioactivity, the Becquerel discovered radioactivity, and there's some findings. Okay, this is all important. And then there are three type of subatomic particles: alpha rays, which is like alpha rays. They call positively charged particles. Beta rays, they are negatively charged. Gamma rays, there's no charge. So if you think about atom has three types of particles, but scientists just found out electrons. So which is um, so the negative, right? But we have to identify two more. So let's see how scientists work on identifying these particles. The Rutherford. The Rutherford is a student of J.J. Thomson, but he wanted to find what are these alpha particles, what are these gamma, where are these in the atom. So he did this experiment, which is he took like a gold foil. This is a gold foil. It's a very thin thing about aluminum foil, and there's a like this is the it's just a screen to detect, and he passed alpha particles through the gold foil. What he notices, majority of the particles going through this foil, but 1 in a 12 million deflects. So you see majority of particles going through. So he came up with the idea that how the alpha particles going through the gold foil, because it's empty. Majority of the atom is empty. But why 1 in a 12 million deflects? Because um, the atom's mass is like mainly condensed in a small area. So that's why whenever it hit to that small area, it deflects back. So this is the diagram. So this is the mass is here, but every other place is like so they can go through it. So Rutherford, it's very important discovery. He came up with the nuclear model. Nucleus, and also he said the positively charged particles, which is the nucleus has positively charged particles, and then later they found out, okay, what is the when they weigh, okay, there's way of the proton, but there's another particle which is neutrons. Neutrons doesn't have any charge, just contribute the mass of an atom. So there are three types of subatomic particles: protons, neutrons, and electrons. Okay. So another important thing is what is atomic number? What is mass number? Atomic number is very important. It shows the sign C. C is a number of protons in a nucleus. Very important is a unique to an element. It defines an element always number of proteins, or if you look at the periodic table, each element is different because number of protons or atomic number is different. What is mass number? Mass number is total number of protons and neutrons. We call that as a mass number. There are several ways we can represent atom. This is a one way you can represent an atom. You write X is an element symbol. Z is the atomic number, number of protons. A is the mass number, protons plus neutrons. So, so this is like if I show you the same thing. So this is hydrogen, mass number, number of proton 1. Um, sorry, atomic number, number of protons 1, mass number 1. What does that mean? Hydrogen has one proton and one electron and one proton. Look at the deuterium, 1, 2. So what is the 2 comes from? The 2 is number of neutrons. So here, 1, 3, and then one proton and two neutrons. You may ask, how can I say that it's always you have a one proton? Always when the atom is neutral, number of protons and number of electrons are same. And also you see this is hydrogen. All the atoms has same number of protons. Same number of protons. So, because that's how we define hydrogen. Hydrogen has same number of protons. So here, always this is 1, 1. That means you don't have any neutrons. If you have 1 and a 2, that means already this 2 is like made out of 1 proton and then 1 neutron. Here you have 1 proton and 2 neutrons. So I have an example. Determine the number of protons, neutrons. I'm sorry, there's something I can see. Let me see. What is the question? Determine the number of protons, neutrons, and electrons in each of the following species. Okay, let's look at one. Okay, so one, chlorine 1735. Chlorine, how many protons? 17. How many neutrons? Use 35. Subtract 17, you give 18 neutrons. And then how many electrons? Because it's neutral. If I don't say there's no charge, that is neutral, so number of protons equal to number of electrons, so 17 protons, 17 electrons. Look at this one. So here, chlorine. I mean, you don't have to you don't need to know chlorine is 17, because if you look at the periodic table, which you can take for the exam too, the chlorine, the mass is, the atomic number is 17. So 17, 37, so you subtract 37, so it's 20 neutrons. Again, how many electrons? 20, because number of protons always equal to the number of electrons in the neutral atom. You look at potassium. Potassium, what is the atomic number of the potassium? I think it's 20. No, atomic number 19, sorry. Atomic number 19. So the 19 protons, 19 electrons, 41. So here you see 41 minus 19, 22 neutrons. So number of protons, 19. Number of electrons, 19. Number of neutrons, always mass number, subtract atomic number. Okay. And then you look at the last one, carbon, 14. How many electrons, how many protons, how many neutrons. So go take the periodic table and see what is the mass number. It's in the, if you look at the periodic table, let me get a periodic table really quick. Okay, so this is my periodic table. You look at the carbon. Carbon in a box has two numbers, 6 and 12.01. So 12.01 is a different number. That is not the mass number. This is but you can find the atomic number. Atomic number is 6. So when we know the atomic number, if I go to my PowerPoint, it is the atomic number is 6. So number of protons 6, number of electrons 6, and number of neutrons you subtract it. Okay, so that's how you find. And also, so now you know what is the mass number, atomic number. I want you to let you know something called isotopes. Every element in the periodic table, majority of the elements in the periodic table, they have isotopes. Isotopes is they have the same number of protons but different number of neutrons. We call them as isotopes. But in the isotopes, there are if you take example 100 gram of carbon, you have these carbon C12, carbon C13. But the amount of that each isotope is different. So in the periodic table, you see the most abundant isotope. So you can say that because you just get the atomic mass. So you take the account all the isotopes in that element, and then you write it list in the periodic table. So now in the periodic table that I showed you, you saw this number, right? Carbon 12.01. Is it a mass number? No, mass number cannot be the decimals, right? It should be 12, it should be an exact number, but this is a decimal. So then the scientists, they took all the isotopes in an element, they took all the isotopes in an element into account, and then they make the mass number. That's how they find the mass number. So if I go here, so carbon has two isotopes, carbon 612, 613, and then each isotope, the mass unit is 12, and this is 13. And then they found the natural abundance of carbon 12 is the mostly abundant element, mostly abundant isotope. So it is 98.93. Think about these two in one sample. You have mostly carbon 12, but you have few carbon 13 too. So that's why we need to take this carbon 13 also to the into account. How do you find the average mass? That is important. You need to know how to find the average mass. What did I do here? Natural abundance given it's a percentage. So when you take the percentage, let me see what I can write. Okay. Let me see. Okay. Okay. Here it is. Okay. So let me see. I can write on it. Okay. So I'm going to write here. If you see isotope carbon 12, I have 12% and then the natural abundance is 98.93. So how, in order to find the average mass, I'm using this color, I'm writing on it. Average mass is, so you take the mass, which is 12 into 98.93 divided by 100. So that's what in the PowerPoint you see 0.9893. If you divide 98.93 by 100, it's going to be 0.9893. Plus you take the other isotope mass, which is 13.0, the big number, 30.003, and then you multiply by that 1.07 by 100. That's what you have the equation 0.01, and then you multiply these two numbers, basically these two numbers, and then these two numbers, and then add it. When you add it, you get the this 12.01, which is you see in the periodic table. Okay, so that's how you find the atomic mass. And then atomic mass you can find using the mass spectrophotometer. So here I have another question. This question: oxygen is most abundant element in both Earth crust and the human body. The atomic mass of its three isotopes, oxygen A 816, 99%, 0.757%, sorry. Oxygen 817, 0.0, very small, right? And then these are very small percentages. And then their masses are the oxygen 816, 15.99. Oxygen 817, 16.99, and then calculate the average atomic mass. Very first thing you need to know, whenever you see a question, you have to simplify it. Don't just scare by looking at the question. So to simplify, first thing I'm looking, okay, how many isotopes in this question? You have three isotopes. Each isotope has its own mass and its own percentage. So you take the isotope mass and you multiply by that percentage. And then you do the second isotope, get the mass, multiply by the percentage. Third isotope, you get the mass, multiply by the percentage, and then you add these three numbers. So let me look at it and see how can I help, how can I do it. Okay, so I'm getting my first isotope, which is oxygen 886. You know why it's 16? Because it's 15.9949. You don't want to write it, right? Because it's a long number, it's a big number. So I have three isotopes. Let me write here. So my first isotope, let me see if I have a good color. I think this is good color. O 816. Sorry. It should be the other side. O, the mass of it is 15.9949 into percentage 99.757 divided by 100. Then I have so then you add this one to my second isotope O 817, which is, you get the mass 16.9991 into 0.038 divided by 100, right? And then you take the next number, which is 0818, which is I'm getting the mass, which is 0.9992 multiplied by 100, 0.205. So I have these three numbers now, okay? And then I multiply this number and then this number, and I added these three. Then that's how I get the atomic mass. So you have it here too, okay? You have it here too, so you can see that. I think that's the end of part 2, and I hope you understand the main things in this chapter: the mass number, atomic number, and how to find the atomic mass of an element. Thank you.